All right, guys, this is part two of representing transformation in a plane. Sorry we weren't able to finish this in class. Um, One of the things that they want you to realize from the activity, so as I mentioned before, whatever's the slide afterwards is basically what they want you to kind of get the idea of. So, what they're kind of trying to have you do on this activity was this idea that the distance is the same. And the other part was, if I go back here, is this idea of how these coordinates shift. So we didn't necessarily go over this in it, but it is really important for you guys to write this down. I'm sorry we weren't able to do that in class, but this is important. So whenever you're talking 90 degrees, what's going to happen is your x and your y switch places. So if let's say I had something like 2 comma 3, this, if I rotate 90 degrees counterclockwise like GeoGebra does, this turns into 3 comma 2, but notice how I changed the sign on the y, so that'll be negative 3. So the next one, if I do it 180, all that happens is, let's use this 2 and 3 again, this will turn into negative 2 comma negative 3. All that's happening is I'm kind of changing these to be negative. These things right here for 180. Now, if I rotate it another, let's do this in blue, rotate again, my x and y switch again. So if I'm doing this 2 comma 3, my x and y would switch again, but this time it would make the 2 negative. So it's a little similar to this one, but the only difference is what turns negative. All right. So this is something you should definitely have written down. It's going to help you a lot during the test, and it's even going to help you on the very next slide. So this slide says, if I'm rotating 90 degrees, what does point C turn into? So I'm talking about point C here. If I'm rotating 90 degrees, I clicked on that by accident. What I would do is I would first switch my X and Y. But remember I said that what used to be my Y, let me make that look like a 7. My 7s always have this little line going through it, guys, in case you're like, well, what's the difference between your 7 and your 2? I always put a little line through my 7 to distinguish it. I had to make my Y negative, or I have to change signs to be more exact. So I'm going to make that negative, and that's how I ended up getting this. I just kind of jumped the gun on it. So this would be if we rotated it to 70 degrees. And right here it shows you what happens when you rotate 90 degrees counterclockwise. And usually we're going to be talking about counterclockwise when we talk about rotation. So the next one, we're going to talk about dilation. Dilation is this idea of something getting smaller. By the way, this is the only type of transformation that is not a rigid motion. Rigid motion. And what I mean by that is it's not like I'm taking this guy here and I'm moving him over here. He's getting smaller. Something else is happening. The distance is decreasing. So, for example, if I was at this point here, this point, he's about, let's say he's a quarter of the size. This distance is going to be 4 times bigger. So I'm decreasing the distance. So it is like I'm moving, but size isn't taking place. So that's why I mean not a rigid, a rigid motion. It's not just moving something. You're not rotating it. You're not reflecting it, and you're definitely not just translating it. So it's the only type of transformation that's not considered a rigid motion because the shapes are changing. So in this goal, we're trying to see these transformations. So let's go into the dilation activity. And it wants us to dilate it. So if we look here, see how it gets bigger? If we go bigger than one, but if we get smaller than one, the shape gets smaller. So this dilation factor is how many times bigger and smaller it gets. This one just goes down to 1/2. You can make it smaller, but they decided to only go to 1/2. So if I go here, this is twice as big. If I go to 3, it should be 3 times as big. And we're going to prove that right now. So right here, it's like, let's have a dilation factor of 1. Let's have a dilation factor of 2. Let's have a dilation factor of 3. And what we're going to do here is we're going to fill these in. So if I'm going to do a dilation factor of 1, or I'm sorry, not 1, I want 2. Obviously, I want something that's not there. So I'm going to change this to 1/2. And if you guys want to know how to put a fraction, what you do is you go to your equation editor and you're going to put 1/2. So you push this big fraction button and you type in 1 over that. You click OK. Now we see a fraction right there. So if I do it at 1/2, my points are going to be, I'm going to look at my A prime and I'm like, okay, so this is my image for 2. I'm going to do the 1/2 first. 0.5 is the same thing as 1/2. I'm doing my 1/2. I'm like, okay, my 1/2 is 1/2 and 1/2. So I'm going to put my parentheses in. I'm going to get 0.5, comma 0.5. Or 1/2, 1/2, whatever way you guys prefer. I'm going to look at my B. So I'm going to go back over here. I'm going to look at my B. And for some reason, I don't know why they're telling you to do your B prime. It's technically your B. They kind of did, oh, it is your B prime. I'm so sorry. So we're going to look at our B prime. So that's 1.5 and our 1. So we're going to do 1.5, comma 1. Just to make it a little more organized, I'm going to make sure that I have my parentheses. I'm going to put a little space in the middle. And then I'm going to do the same thing for C. So C, I'm going to look at my C prime. It's 2, comma 0.5. So this will be 2, comma space 0.5. Put in my parentheses. If you want to make it look nicer, you can put a little 0 here. I didn't do it over here, but I can. It just makes it look a lot nicer. And we're going to do it for 2. So again, guys, I'm not going to go over the entire activity, but what I would do is I would slide this to 2, and I would write this down. So I would write down the 2, comma 2. So this becomes 2, comma 2. This one is going to be 6, comma 4. Trust me, all we're doing is just doubling the coordinates. This one would be tripling it. So this would be 3, comma 3. This one would be 9, comma 9. And if you don't believe me, you can always just do it right here and figure it out from right here. So it makes it a little easy because you're using this little tool right here. All right, so moving on to the next one. What is the relationship between that and the vertices? So like I said, this means we're going to multiply it. So what we're going to do is we're going to say that we multiply n. N, remember, is our scale factor, how big or small we're going, times the coordinates. By coordinates, coordinates. By coordinates, I'm referring to the x, comma y. My x coordinate is my y coordinate. So we're going to multiply it by the x, comma y. So we're multiplying it by the coordinates to get the new image. And one thing that I haven't gone over too much, guys, is this is known as the pre-image. This is known as the new image, but usually both in the package and Admentum, it's known as the image. So that's just what we call it. We call our transformation the image. So we multiply this to get the image. So whatever our A is, we're going to multiply it by times n, and that's going to give us our A prime. All right, this next one is like, okay, let's measure the lengths. All right, I'm going to use the same numbers. I'm going to use 1/2. I'll just put 0.5 this time. I'm going to use 2, and I'm going to use 3. So I'm going to go back to my triangle over here, and I'm going to measure the distance. So I'm going to measure from A to B, from A to C, and I'm also going to measure B to C. And I'm going to do it for all of these too. All right. And what I would notice here is I'm going to do it for 3. You guys can do it for the rest. For 3, I'm going to get this AC, which is 3. So if I'm doing AC, A to C, that's what we had here for the 3. This all of a sudden became 9. If I'm doing my BC, that's my 1.4. So right here, this is my BC, my little a, in other words. See how, let me move these around. My little b is my 3, my little a is a 1.4. So 1.4. But here I'm going to call it my little a prime, so 4.2. So I'm going to change this to 4.24. 4.24. And the last one is going to be 6.7. So I'm going to change this to 6.71. All right. So that's how I would do this. And I would do the same thing when I scale this down. Also, I believe if you look over here, it'll tell you the lengths. A prime, B prime, C prime. So even if you don't want to do this whole area thing, you can literally just check right here and it gives you the lengths. You don't even have to do the measuring thing if you don't want to. So right here, if I wanted to do it for 2, here's my answer for 2. I can scroll down to get to C. I don't want to scroll down because that's going to move these little circles. All right, so the next thing we're going to do is it's going to say, what do we notice when we go from 0 to 1? So what happens here when we go from 0 to 1? In other words, it's asking, what happens when we're at a fraction? Well, when we're at a fraction, we get smaller. Everything gets smaller, right? So when scale factor is a fraction, the image gets smaller than the pre-image. The first thing. Our next one's going to be when the scale factor is greater than 1, the image is larger than the pre-image. So basically, if we're at a fraction, it's going to get smaller. If our scale factor is bigger than 1, it's going to get bigger. That's all we're saying. Now we're going to talk about the angles. Now the cool part about the angles, let's see. Oh, this one doesn't measure angles. So what I'm going to do here is I'm going to delete all of my distances because I don't really need those anyways. I'm going to make this bigger so it's easier to measure. So I'm going to do all of my angles. So give me a second while I do all these angles. It's such a force of habit to say give me a second because I realize it's like there's no one here. I'm recording this on my own. So then I'm going to go here counterclockwise. So I want to go from A to C. So I'm going to go A, B, C. I'm going to do the same thing here. I have to zoom out. And then I want to go from A to B. I want to go from B to A. Oh, wait. I want to go from B to C to B. Sorry. Counterclockwise. Counterclockwise. Boom. So if I look at my actual angles, I believe they give me a measurement right here. I'm going to assume that alpha is going to line up with, oh, no, I thought I was on an arrow. So my gamma is matched up with this. I forgot what this one's called. I want to say that's a lowercase delta. Okay, so gamma matches up with delta. So if I go over to my angles, my gamma and my delta match up. Do they though? I don't have them in any order, guys. I'm sorry. But the important thing is I'm going to use different colors to show it. I should have done these all in order so you guys could see it. I should have gone angle A, angle B, angle C, and then angle A prime, angle B prime, angle C prime. But the main idea here is, look, our angles stay the same. So the idea here is that angle A corresponds with angle B. So basically when you're doing dilation, so when I'm doing this, whatever I put here, so I'm going to write down whatever I got here. So my angle A is 26. I'm just going to call it 27. I'm just going to round up, guys, just to make it easier. So this is 27, which means this has to be 27. Over here, I'm looking at this angle B, which is 108 degrees. So I'm going to say that's 108. That's 108. And then I'm going to go to the last one, which is 45. And I'm going to say this is 45 and this is 45. And it doesn't matter what my scale factor is. In this case, my scale factor was 4. Even if I do it down to 2, notice how those angles, the yellow angles, still match up. So literally, you could just go down to 2 and you're just going to copy it. So what can you conclude from this? So what you would say is dilation does not change the, I'm going to say corresponding angle, because they are different angles. So, but they're the corresponding angles. And then here, this is a reduction. Um, so reduction or change in size. So this one, we're just kind of doing this. So is this a reduction? So if it's our scale factor is 1, no change in size. That's exact. 1 is the exact same thing. No change, not no change. No change in size. Does the image rotate? So this one we would say no. It doesn't change. It doesn't rotate. If we read this, it actually says if it's negative, that's when it kind of does this 180 rotation. So right here, it doesn't let me go to negative. Let me see if I can make it negative. I might make some changes here. To see polynomial. Where's my bar? Is there any way I can change this? Change the settings. Okay, cool. It does give me a min and max. I'm going to change this to like -10. I'm going to change the max to +10. You guys don't need to know how to do this. If you do want to know how to do this, set an appointment with me. I can show you how to do it. But now you can see it goes down to negative. So I'm going to go down to like -3. We see that it's 3 times bigger and it rotated 180 degrees. So this one, it's bigger than 1. So this would be an enlargement. It's getting bigger. And it does rotate. So anytime you see these negatives, it is going to rotate. This is less than -1, but that makes sense because if we're looking at a number line, -1's here. If we get smaller than it, we're going to go this way. So the negatives get a lot bigger. So that's all we're doing for this one. Basically, all the negatives are going to be yes. If it's equal to, there's no change in sign. If it's a fraction, this right here being a fraction, that means that we are going to, that means it's going to be a reduction. If it's, in this case, less than, but less than in this case kind of means greater than because our negative numbers are kind of getting bigger. That's going to be an enlargement. And then self-evaluation. Let me know how you did on this one. And then this is what we're talking about here. As we're doing a scale factor, the distance from here to here is going to double. So if our scale factor in this case is 1, if our scale factor is 2, this distance doubles. It's 2 times as much from wherever we're dilating from. So this is what's known as the center of dilation, how far we're getting away. So every time you make something bigger, there has to be a center of dilation where you're doubling or increasing. All right. And then this one, all right. So if we're going from here to here, notice how, let me get my highlighter out. This and this is about 4 times bigger. So that tells me that we're making this bigger by 4. So we know it's an enlargement, but we know it's not a factor of 4. A fraction doesn't make things bigger. So that means that has to be an enlargement with a factor of 4. From the origin, I think for the most part, we're going to be doing enlargements from the origin. Moving on. So from here, we're making it smaller. So here's the thing. This is a lot harder to do. So what you always want to do is you want to put your new divided by your old. That's going to determine your scale factor. So in this case, our new is 1.3 divided by 3. And we can verify this by just double checking if this works. If these two are equal, then it is scalable. So let me pull out my calculator. 1.2 divided by 3, 0.4. Let's double check if that's right. Yep, 0.4. So that means our scale factor is 0.4. What's our scale factor of dilation? And 0.4 is another way of saying a fraction. So that's how come it's getting smaller. Horizontal and vertical stretches. So I'm gonna have to make a third video on this, guys. I'm so sorry. I'm just crunched for time right now. But the third video will be out tomorrow, 8/19. I'm just really crunched for time. I'm so sorry. Normally I try to get these modules done in one unit, but luckily the last video is going to be very, very small.